Okay, welcome everyone. So this is a rescheduled discussion hour that we are having because I actually will be traveling this Saturday. So that's the reason why, I thought of taking this discussion session today. That is from 7 to 9 p.m. And I believe you have already been intimated about the same in the course website and also, through emails. So, okay. Again, apologies for, letting this know in a short notice, but, it's basically some traveling that came to my end, and that's the reason why I actually need to reschedule this. So let's get started for today's discussion problems. So what we'll do is we will quickly recap on what we actually did in the previous week. Basically, we were actually trying to focus on evaluating the velocity field of a rotating porous cylinder. And so we saw that, so we argued that this is going to be a two-dimensional flow because of the fact that we now have two components of the velocity field, ur and u theta. But we argued that because of since the fact, I mean, because of the fact that the cylinder is infinitely long in the z direction, and of course, using the axisymmetry assumption, we said that the velocity fields, although they are going to be two velocity field, that is ur and u theta, they are simply going to be functions of r only. Again, due to the fully developed and axisymmetric assumptions that we invoked. Okay, and then our idea is to calculate this velocity field, and for that, again, as we had been doing repeatedly, we use the non-dimensional approach. We had certain scales that was given to us. For instance, the characteristic velocity scale in the r direction was given to be equal to the magnitude of the suction velocity, while the characteristic velocity in the theta direction is equal to the rotational velocity at the cylinder surface, basically, which is omega times a, where omega is the rotational velocity of the cylinder. And the scale for pressure, it was a viscous scale that we took. Sorry, it was the inertia scale that we took, which is rho times of the characteristic scale for velocity squared. And for here, we took the scale to be u theta c. That is, the pressure scale is dependent on the pressure scale is chosen with respect to the characteristic velocity in the theta direction, which is u theta c. And from here, we evaluated what will be the scale of pressure, which is simply going to be equal to rho times omega squared times a squared. And the obvious length scale that we had was the radius of the cylinder. Okay, sorry for that. Okay, so the idea was to write down the boundary conditions in first using writing down the dimensional boundary conditions, and then what we did is we used the scales to write down the non-dimensional versions of the boundary conditions. And similarly, the same thing that we did is for the r momentum equation as well, because see, we are required to find the ur and u theta velocities, and also recall that pressure was unknown here because it was given that we were asked to calculate the pressure field given there was a prescribed pressure at r tending to infinity. Okay, which means that the pressure was also unknown. So we said that we are going to get these three unknowns from the three equations that we had, which is the r momentum equation. So first is the r momentum, the theta momentum, and the continuity equation. Okay, so these three equations will should in principle give us the three values of the unknown ur, u theta, and pressure. So what we did is we used the same principle. We started off with the dimensional r momentum, and I used the characteristic scales that we had to derive the non-dimensional form of the r momentum, which looked something like this, where we had all the non-dimensional variables, as you can see, and we had certain ratios. For instance, we encountered a parameter u tilde, which which is a ratio of this quantity omega a by u, where we can say that this is nothing but the strength of the flow in the theta direction. So you can interpret as, physically you can interpret as like the strength of the flow in the theta direction to the strength of the flow in the r direction, which is due to suction. So in a way, it says u tilde basically says that how strong is the rotational motion of the fluid with respect to the radial suction that is taking place at the interface. Okay, and I believe you can note, you can see that this u tilde is indeed a non-dimensional number because omega a and u has got the same dimension for velocity. Okay, and also we encountered something known as re, which was nothing but the Reynolds number defined with respect to the suction velocity. So we call it as the suction Reynolds number. And apart from this, so this RE and U tilde, these are just non-dimensional numbers. And then we had all those parameters which are just simply non-dimensional, which is UR and pressure basically here. And I guess we also have U theta in this equation as well. But now this is non-dimensional, okay? So that was the non-dimensional R momentum, and I said that what you can now do is you can do the similar exercise, that is writing the theta momentum equation dimensionally and invoking all the characteristic scales and the non-dimensional numbers that you get as a result in order to get the theta momentum equation, which which basically takes this following form, okay, where you can see that. So remember, we have invoked all the assumptions that we considered. For instance, the flow is axisymmetric and the flow is fully developed, and things like that. And then this is the final form of the non-dimensional. I hope you can see that this is the final form of the non-dimensional theta momentum equation, which again you get in terms of these non-dimensional variables, and also you have the suction Reynolds number in this form. So I gave you the hint to actually solve how to basically solve for a velocity field after that. But what I will do is just to formally close this problem, I will just show you the steps, show you certain steps which are important, which I feel is necessary. And you can then compare your answers with whatever I do here, and then verify if they're actually correct or not, okay? So so what we require to do is we require to solve. So it's now just boils down to the fact that we require to solve this equation 1, and maybe I'll call this as equation 2. So we just require to solve this equation 1 and equation 2. But I hope you realize that this is where we encounter a little setback, because apart from this UR and U thetas appearing in equation 1 and equation 2 being unknowns, we also have a pressure term that is appearing in the R momentum equation, which is also an unknown. Okay. So then basically just three equations. And as I said, that since there are three variables, okay, so since there are three variables, I should say, that means we also require one more equation, which will come from the continuity equation. And let's then write down the continuity equation. So I also wrote down, by the way, I wrote down the continuity equation, but anyway, I will write it down once again, just for the sake of completeness. So the continuity equation, so I hope you realize that we also need one more equation now in order to get the three unknowns. So that equation will come from the continuity equation, which will then close the system. So the continuity equation, if you write in cylindrical coordinate, invoking all the assumptions that your flow is axisymmetric and fully developed, it just boils down to this thing, which is del R of R times del U del R, where this R and UR, these are all non-dimensional numbers. So basically this is the non-dimensional non-dimensional simplified continuity equation. I hope that much you can understand from this from this equation. Okay, so maybe I'll call this as equation 3. So what we need to do is we need to so this then hints us that we can actually evaluate UR if we integrate equation 3. Okay, so then let's try to do it. So if we integrate, so if we integrate with respect to R, of course, then you can see that we get what? So we get, yeah, just 1 second. Just 1 second. I'm just comparing the certain things with respect to my notes. Okay, so I have this. Yeah, so I believe you can just integrate. So what I was doing in my notes is, initially I was just applying, I was just using the product rule basically to break this and then integrate it. So what you can do is you can also simply direct integrate. I don't see a problem here. So if you integrate, what you will get is so you are so remember, UR is just a function of R only. Okay, so UR is a function of R only. Okay, which means I can rewrite equation 3 as now as ddr of R times UR, which means I have replaced the partial derivatives with the complete derivative, because I know that UR is just a function of R. And then if we integrate, uh, what will we get? So we'll get RUR is equal to some constant C1. Okay, so simply what you get is you get UR equal to some C1 by R. That's it. That is as simple as it gets, because it's just the first order ODE. So you just need to integrate, which is in exact form. So it's just an integration that you need to do, and that's what you get UR as a function of R. But remember, we require to find the C1 from the boundary condition. So what we'll do is we actually have two boundary conditions in principle. One was that my UR at R equal to 1 is equal to -1. You recall, because of the fact that we actually had a radial suction, which is actually taking the fluid inside the surface of the cylinder, and that's the reason why we have a negative radial velocity at the interface of the cylinder. And we also had one more condition, which is the fact that my magnitude of UR when this R goes to infinity, this is equal to 0, and this is trivially satisfied because I know that when my 1 by R basically goes to 0 as R tending to infinity. Okay, so this condition is trivially satisfied by 4. This is trivially satisfied by 4, since I know that. So since 1 by R, this approaches 0 when R approaches infinity. Okay, which means I just require to use this boundary condition in order to evaluate C1. And if we use this, so what do we get? So we get -1 is equal to C1 by 1. And this implies that my C1 is just going to be equal to -1. So which means that my radial velocity field is just -1 by R. That's it. That's my radial velocity field that we get from the continuity equation. So I believe you can understand that just from the nature of the problem that you are solving, you can actually get the velocity field. You can actually get the R velocity field from the continuity equation itself without having to solve for the momentum equation. So this is, I mean, the problem is framed or designed in such a way that this happens. And one more, I mean, effect or one more consequence of this of getting UR from the continuity equation is get we also we basically need the pressure in we also need pressure as a solution of our problem, right? Which means the continuity equation should give you at least one unknown so that we can calculate the two unknown from the R momentum and the theta momentum equation. And the unknown that we get from the continuity equation is the R direction velocity field, simply by integrating it with respect to R1s. Okay, so that's it. That's your R directional velocity field. Okay. Now, as I said, what we will be doing is we will try to evaluate the theta directional velocity field. Remember, we also need to calculate pressure. But if you closely look at the R momentum equation, see, now we have UR with us. These U tildes and Reynolds number, these are just parameters, which means I now require to calculate U theta and pressure. So just by having UR won't do any good to us because we don't know U theta and pressure that we can solve from equation 1. Okay. So for that, what we'll do is we'll take the help of equation 2, because I know that in equation 2 I don't have pressure. I just have U theta and UR in equation 2 as variables, and I recently calculated that UR is just going to be equal to -1 by R, which means in principle if I substitute UR in equation 2, I must get an equation which governs U theta solely. Okay, so that's what we will do. So substitute UR equal to, or whatever is this, like substitute UR, which is equal to -1 by R in the theta momentum, sorry, in the theta momentum equation to solve for U theta. And I believe now you can actually think that once we know UR and U theta, we can then, I mean, once we get U theta by solving the theta momentum equation, substituting the value of R, and we get U theta, then what we'll do is we'll take UR and U theta and put it in the R momentum equation to basically get the solution for pressure. And that's all that we require to do in this exercise. Okay. So okay, so let's then first solve for U theta. So what's the theta momentum equation? So this is the theta momentum equation, right? So this is basically your theta momentum equation. So let's write it down once again such that you can understand it more clearly. So okay, so this is your so this is the theta momentum equation. So it is UR times del u theta by del r plus u theta ur by r, and this is equal to 1 upon Reynolds number times 1 by r del r of r times u theta by r minus u theta by r squared. And we will use the fact that this ur is going to be equal to minus of 1 by r, and then this ur is also going to be equal to minus of 1 by r. So if we substitute, let's see what do we get. Okay, so let's try to see what we get if we substitute ur equal to minus 1 upon r here. Okay, so what do we get? So we get minus of 1 upon r times, see, remember u theta is also a function of r only, okay? Which means I can then replace all the partial derivatives with total derivatives, which means I can replace, this basically means that I can replace del r with equal to ddr as a consequence. So this becomes d of u theta by dr minus u theta by r squared. That is something that you get. And then if I simplify this, so what I'll do is I'll first, simplify this term and then, put the Reynolds number there. So this term upon simplification will give you what? So it is 1 by re del r of r times this. So it is going to be equal to 1 by r du theta by dr plus d2 u theta by dr2. So what I'm doing is I'm just applying the product rule, taking into this factor 1 by r, okay? So first this one will get differentiated, which means I'll have 1 by r d of u theta by dr, and then I'll leave this one as constant, and this one will get cancelled, and I'll get d2 u theta by dr2, okay? And then I have minus u theta by r squared as well, okay? So I have this u theta by r squared here. Okay, I think this is fine. Okay, then what I'll do is I'll take in the Reynolds number in each term, which means I will have minus of 1 by r du theta by dr minus u theta by r squared. And then I'll have 1 by re times 1 by r du theta by dr plus 1 by re times d2 u theta by dr2, okay, minus I'll have 1 upon re times u theta by r squared, okay? So now I believe you can see that we have a term which is second derivative in u theta, we have a term which is first derivative in u theta, which is basically these two terms, and then we have a term which just involves u theta. So what I'll do is I'll pick these terms here and I'll just segregate the different derivatives or different orders of derivatives of u theta, and let's see what we'll get. So we'll get a very, nice little ODE which we are actually familiar with, and we will see. So then what we'll get? So we'll get 1 upon re. So let's see what we'll get. Okay, so this is 1 upon re. I'll just take this term, which is d2 u theta by dr2. Okay, and then I will have so this is, so when I take this term over there, I'll have 1 by r d2 u by d theta times of this term, which I will write it as so this term I'll write it as 1 by r du theta by dr times 1 plus 1 by re, okay, because I'm just taking this term over there, that's all that I'm doing here, okay? And then I'll have the other term, which is u theta by r square times 1 plus 1 by re, and this is equal to 0. So this we get when we take this term to this side and then take u theta by r squared common. Okay, so now what we'll do is so this term I can simplify as, if I take re in the re as LCM, then I'll get re plus 1. Okay. And this term will also give me Re plus 1 by Re. This term will also give me Re plus 1 by Re, which means I'll have an Re in all the denominators here. I'll have an Re here, I'll have an Re here, and I'll have an Re there, which means I can just take this Re out just by writing this equation as d2 u theta by dr2 plus okay, I'll write this as 1 plus Re by r du theta by dr, and I'll have plus, okay, so what will I have here? Let's see. Okay, so this time it's a minus. Oh, hold on. I think I did a mistake. So remember, there is a minus here. Okay, so there is a minus here, which means this term will be 1 minus Re. Okay, this term will be 1 minus Re. So this term will be Re minus 1 then. Okay, just check the sign. This term will be just Re minus 1. Okay, so this term will then be equal to uh, Re minus 1 by r squared times u theta. Okay, now what we'll do is we will multiply the equation by r square, multiply by r squared. And if we do this, let's see what we'll get. So this is r square times d2 u theta by dr2 plus r into 1 plus re times du theta by dr plus re minus 1 times u theta is equal to 0. So that's it. That's the simplified equation that u theta is governed by if we substitute the fact that ur is equal to minus of 1 by r. Okay, and little bit do some analytical manipulations in order to get in order to get this simplified form. Okay, so now tell me if you pay a little bit of closer look what this equation looks like. Okay, so this equation is nothing but your Euler-Cauchy equation, as I was telling, as I was hinting for you in the last class, that eventually you will get an Euler-Cauchy equation which governs u theta as a function of r. Okay, so this is an Euler-Cauchy equation, and or sometimes it is also known as equidimensional equation, as we saw. So this equation I believe we also saw when we were actually trying to solve for the time periodic pressure driven flow. If you remember, we were trying to solve for a time periodic pressure driven flow in a cylindrical channel, and we saw that the u hat of r, the equation which governs u hat of r, typically came out to be an Euler-Cauchy equation. Okay, yeah, if hmm, I think that I, I don't know, maybe. No, I think no. In the time periodic pressure driven flow, I think we got modified Bessel's equation. So somewhere, I mean, I don't recall exactly where we got, but somewhere, I mean, we got this form of the Euler-Cauchy equation when we were solving. I think we got it there when we were actually trying to solve this problem. This rotating cylinder problem. So your cylinders are rotating with omega 1 and omega 2, and we are actually trying to find out what is u theta as a function of r. I think in this problem we saw the Euler-Cauchy equation. Yeah, exactly. So sorry, yeah. So sorry for that. So in the in the transient oscillating pressure driven flow, we actually got something which is known as a modified Bessel's equation. So we are writing, remember, we were writing J0 and Y0s for the solution. And then we took the real part of whatever we got actually. But in the rotating cylinder, we actually got this form of the Euler-Cauchy equation. Anyways, that is it's just some recapitulation that we did. But so yeah, so once we so now it is well known, right? Because since this is an Euler-Cauchy equation, we know the solution from, right. So we assume u theta to be of the form some r power k. Therefore, du theta by dr is just going to be equal to k times r power k minus 1, and d2 u theta by dr2 is going to be equal to k times k minus 1, sorry, k times k minus 1, r power k minus 2. Okay, and what we do is we just substitute it here, which means from the first term I'll just get k into k minus 1 times r power k, and from the second term I'll have k times r power k 1 plus re. Okay. Okay. And from this term, I'll just get Reynolds number minus 1 times r power k. Okay. So what we are doing is we are just substituting this terms and this terms in this equation. So for instance, in the first term, I'll have k into r power k minus 1. Okay. Sorry. In the first term, I'll have this term, which is k into k minus 1 multiplied by r power k minus 2, and I have an r square basically. So this term will just give me k into k minus 1 multiplied by r power k plus 2, and minus 2 will just get cancelled. Okay. Similarly, drawing the same analogy, in this term we'll just get k into r power k, and there is 1 plus of Reynolds number here. Uh, okay. And similarly for this term, which means I can, and of course this is equal to 0. And then what I can do is I can take r power k as common, which means I'll get k into k minus 1 plus k times 1 plus of re, okay, plus re minus 1 is equal to 0. And then I know that r power k can't be equal to 0, right? Because if r power k is 0, then u theta is 0. But this is not possible, right? Because the boundary condition mandates that at r equal to 1, your u theta is omega times a, which means the only possible uh, option or the solution to the above equation is that k into k minus 1 plus k into 1 plus of re plus Rd minus 1. This is equal to 0. And this is just a quadratic equation, right? Because this is k square minus k plus, maybe I'll write it as k plus Rek plus Rd minus 1 equal to 0. Which means this k and this k will just get cancelled. And I have an equation which governs k, which is quadratic, of course. And this is k square plus Re times k plus Re minus 1, and this is equal to 0, which means my solution for k will be minus the Reynolds number. It is going to be minus b plus and minus of square root of b square minus 4ac by twice a. So this is going to be minus Re plus and minus of square root of b square, which is Re square, minus 4. A is 1 and c is equal to Re minus 1 divided by twice a. Yeah, that's it. That's the solution for k. Okay, so let's see what we get. Let's see the roots. So this is minus Re, where I hope you understand that Re is your suction Reynolds number, which is rho times u, the suction velocity, times a divided by mu. Okay, so this was your suction Reynolds number typically. I just keep this in mind. Okay, and this is just a non-dimensional number. Just writing it down, just the suction Reynolds number. Okay, so then let's simplify this. So this is square root of Re square minus 4Re plus 1, which means I can then write this in the term of a squared term. Going to be minus Re plus minus square root of, this is going to be Re minus 2. Sorry, Re minus, okay, this is going to be 4, right? This is not 1, this is going to be 4. See, that's because this is minus Re and this is minus 4, and there is a minus 1, which means I'm going to get 4. And then this is going to be Re minus 2 squared, okay, by 2, which means I should get k to be equal to what? So k should be equal to minus Re plus and minus Re minus 2 by 2. So if I take the plus sign, if I take the positive sign, I will get k1 to be equal to what? K1 to be equal to minus 1, I believe, because minus Re and plus Re will get cancelled, and minus 2 and minus 2 is going to be minus 1. Minus 2 and 2 is going to be minus 1. And if I take the negative sign, okay, I will get my second root as 1 minus Re. Why? Because this is going to be negative, so this is going to be minus 2Re minus 2 by 2. So 2 will get cancelled from the numerator and denominator, and then I'll get this 1 minus Re basically. Okay. Or is it going to be 1 plus Re? Let's, okay, hold on. Let's just check. Okay, so it's going to be minus Re minus 2Re minus 2 by 2. Okay, so it is going to be minus RE minus 1. Okay, yeah, so it is going to be actually 1. Did I make any mistake here? So the plus sign is going to give me minus 1 and the minus sign. Okay, when I take the minus sign, okay, see there's a bracket here, right? So yeah, so it's exactly. So if I take the minus sign, if I take the minus sign, I'll have minus RE plus 2 because there is a minus sign already embedded in here. So then this is going to be equal to 2. So this is going to be equal to minus 2RE plus 2 by 2, which is going to give you 1 minus RE basically, if you just cancel 2 from the numerator and denominator. Okay, so that's it. Then the two solutions is going to be linear combination of k1 and k of the roots involving k1 and k2. So the solution for u theta then is going to be some, let's say a1 times r power k1 plus a2 times r power k2. Okay, and then u theta is going to be equal to a1 times r power k1 is equal to minus 1. So this becomes r power minus 1 plus a2 times k2 is equal to 1 minus re. So this becomes r power 1 minus re. Okay, so that's it. That's your solution for u theta. Okay, maybe I'll name this equation. What do I name? So this is 4. Maybe this is 5. Okay, and maybe this Euler-Cauchy equation, we'll call it as 6. And the solution, the complete solution, we'll call it as 7. Okay, so now let's use the boundary conditions that we have on u theta. So what I have is that u theta, okay, so this is, okay, so this is not, okay, so the boundary condition that we had is u theta at r equal to 1 is going to be equal to omega times a, and the second boundary condition is u theta at r tending to infinity is going to be equal to 0. Okay, so if I use the first condition, okay, so okay, what I'm just thinking, okay, let's not use the first condition first. So let's keep this condition for a hold. But if we use this second condition, I know that, see this quantity. So now let's have a look at this quantity r to the power of 1 minus r, because this is little bit of a critical number. Why? Because the behavior of r to the power 1 minus r actually depends on the value of re. Okay, so I know that if I use this boundary condition that u theta at r tend to infinity is 0, then for any Reynolds number, Reynolds number that is less than 1, I know that 1 minus RE is going to be equal to, so if Reynolds number is less than 1, 1 minus RE is going to be equal to greater than 1. Okay. Is it? So if Reynolds number, yeah. So if Reynolds number is less than 1, then 1 minus RE is going to, okay, sorry. So 1 minus RE, hold on. So if RE is less than 1, let's say it is some 0.8, so 1 minus re is going to be 1 minus 0.8, which is equal to 0.2. Okay, yeah, so then 1 minus re is actually going to be equal to greater than 0. Okay, which means for the boundedness condition to be true, so if this is the case for u theta at r tending to infinity equal to 0 to be true, okay, I require that a2 has to be equal to 0. Okay, this is a must for the case when Reynolds number is actually less than 1. Why? Again, because since r power a is going to, so a is basically going to be greater than 0 if my Reynolds number is less than 1. Again, because of the fact that, see, you just substitute a value which is less than 1 here, and then you will see that this number is positive, which means if in order to have u theta to be 0 at r tending to infinity, I must have a2 to be 0, otherwise this is simply not possible. Okay, because this factor will basically blow up at r tending to infinity because of the fact that Reynolds number is less than 1. Okay, which means that the u theta is just going to be equal to a1 times r power minus 1 when Reynolds number is less than 1. Okay, and then if I use this boundary condition now, if I now use this boundary condition, I have now that u theta at r equal to 1 is equal to omega times a, which means I can have omega a equal to a1 times 1, okay, which means a1 is just going to be equal to omega a, okay. Oh, sorry, a1 is just going to be equal to 1 because we are just doing this non-dimensionally, okay. So this is 1, yeah, because this is just non-dimensional, right? This is just at, so u theta at r equal to 1 is just 1, because remember u theta, the dimensional is omega times a, and we have chosen the characteristic u theta c to be also to be equal to omega times a, which means that u theta is just going to be equal to 1, okay. This means that a1 is just going to be equal to 1, okay. A1 is just going to be equal to 1 for, but you need to realize that this is true for any Reynolds number which is less than 1, okay. So this means that my u theta, the solution for u theta is just going to be equal to, so a2 is 0, a2 is 0 and a1 is 1, which means u theta is going to be equal to 1 by r, okay. So this is the solution for u theta. This, is the solution for u theta when Reynolds number is less than is less than 1, okay. So okay, so I think, yeah, I think this is fine, okay. So then we also, so now you have both the velocities, right? We also have ur and we also have u theta. For instance, ur is equal to minus 1 by 1 by r, and u theta is going to be equal to 1 by r basically, okay. But realize that this form of u theta is only possible when your Reynolds number is less than 1. And remember, I told you that for Reynolds number greater than 1, at least with the boundary condition that we have, we cannot actually write analytical solution, typically because then u2 can be any non-zero number, which means these two boundary conditions are not actually sufficient to give you the exact value of u2 if your Reynolds number is actually greater than 1, okay. So for Reynolds number greater than 1, we need some other boundary conditions, maybe. So there is something known as circulation, so you can define circulation, and then so that up to Reynolds number less than 2 you can find an analytical solution, okay. But for greater than 2, for this problem you actually cannot find an analytical solution, because you cannot determine the exact value of a2 from the given boundary conditions that we have in our disposal, okay. So I hope you can realize that you can only find an analytical solution in the case, at least for this given boundary condition, when Reynolds number is less than 1, okay. And when Reynolds number is greater than 1, I hope you can realize that this quantity r, the 1 minus re, is going to be less than 0, which means that this quantity will not blow up anymore, which means I do not have a condition on a2 now, and a2 can be any generic number which cannot be obtained precisely from the given boundary conditions that we have, okay. That's the reason why I said in the last class that you cannot determine analytical solutions when Reynolds number is actually greater than 1 in this scenario with the given boundary condition that we have, okay. Yeah, but as I said, you can also enforce something known as circulation, and for if you use the definition of circulation, then you can, so that you can find analytical solution up to Reynolds number equal to 2, right? In fact, Reynolds number, for you can get an analytical solution for Reynolds number less than 2, okay. Okay, all right, so that's it. That's, so now you have u theta and ur. So now all you need to do is substitute u theta and ur in the r momentum equation to get an expression for pressure. That's all that you need to do, okay. So substitute uh, u theta and ur in the r momentum equation to solve for pressure. That's it, okay, which is p as a function of r, okay. So I'll not do this you, I believe you can do it at your end. Instead, I'll just give you the expression for pressure which I have. So what you will get is, you will get pressure as follows. So p of r will be equal to 1, so it will be some p naught, which we know p naught is given to us, plus 1 plus u tilde squared by u tilde times 1 by 2 r squared, and there is a minus, there's actually a minus sign over here, okay. So this is what is going to be your pressure field. So this is going to be your pressure field, And I'm not showing the algebra. You can just substitute the value of ur and u theta and then just solve, integrate it, and then integrate with respect to r ones, because you have del p del r in that equation, from which you will get an explicit expression for pressure, which is just as this. Okay, so this is the pressure field. Again, this is true for again I say this is true for Reynolds number less than 1, because of the fact that we are using these two forms of the velocity field. Okay, so that's it. That's your pressure field. Okay, and that is your velocity field for this problem. Okay, all right. So I believe this is okay, and those of you who have tried, please match your answers. You should get for Reynolds, as I said, for Reynolds number less than 1, you should get your velocity field like this. For pressure, you should get your pressure field as this. Okay. Again, I hope you can realize that how do you get pressure is that we just take these values of ur and u theta, substitute it in the r momentum equation, which is this, and then just integrate it once, because we have del p del r, and use the fact that when r equal to infinity, or when r basically goes, when we are approaching far field, my pressure is p naught. Okay, that's all that you require to do, and uh, that will give you the unknown that you are going to, I mean, the concept of integration can be obtained from that boundary condition, and then you can then derive this explicit expression for pressure, which takes the following form. I'm not doing this because this is just substituting value and just merely integrating it. That's it. And I believe you are, well capable of doing this at your own. Okay. Okay. So indeed, you can see that when r tends to infinity, my pressure basically goes to p naught, which is actually what we have as the boundary condition for pressure. Okay. And this is the disturbance that is being generated because of the rotation, because of the combined rotation and the radial suction that is taking place uh, that is taking place near the vicinity of the rotating cylinder. Also, what you can see is uh, see u tilde is just, oh, what is u tilde? U tilde is omega a by u, right? That's how we have defined u tilde, which means this is going to be a positive number, because omega is positive, is the rotation velocity. U is the magnitude of the suction velocity, which means it is positive, and A is anyway positive, which means that this quantity is always going to be greater than 0. Okay, and this quantity is also going to be greater than 0, which means that this quantity is positive. Okay, which then means that you can think about it like that near the cylinder. So this is something interesting. Okay, it just came into my mind just now, that near the cylinder, if you basically look into what is actually happening near the cylinder, you know that at far field, at r tending to infinity, you know that your pressure is just p naught, right? You know that if you just take a invincible annulus of fluid, you know that your pressure is p naught. And near the cylinder, maybe in these zones, maybe I mean, maybe what to say, maybe in these zones, maybe in this zone of the fluid, okay, you see that your pressure field is actually less than p naught, right? Because this entire quantity is actually positive. Okay, which means that you are kind of having a suction, and this is obvious, right? Because you are actually having a suction at the interface, at the surface of the cylinder, which means that you are bound to get a less pressure with respect to the ambient pressure, and this suction should actually then drive the fluid which is at bulk to move towards the region where you are having low pressure, right? Because the fluid will try to move into zones, into pockets where they will see a lesser pressure. That's how because you will basically get a pressure gradient in that direction, and this I mean, this is how it basically comes out as a solution of the problem, typically because you're also having a suction, which means that the fluid needs to come from a region and then penetrate through the surface of the cylinder, which means that naturally you are bound to get a low pressure with respect to the far field pressure, which actually creates a gradient which drives the flow from the bulk towards the surface of the cylinder. Okay, this is something that you can interpret from the expression of pressure. Okay. All right, that's it. That's this problem. So I felt this is a nice little physically realistic problem, and you see such kind of flows in many real life situations as well, as I discussed it in the previous discussion hour. So we are just trying to understand the fluid dynamics of the problem. That's it, using some simplified analytical solutions that we had at our disposal. Okay. Okay, all right. So with that, maybe we'll stop this. We finished that chapter actually, which is 2D flows. I have not covered one part, which is known as the lubrication theory. Actually, there aren't any much problems that we can do from the lubrication theory. So it suffices just to look into the lecture videos of lubrication theory, and that is sufficient for you to answer the problems in the assignment that you are supposed to have for this week, that is week 7. And yeah, so and then with the knowledge of all the flows that we learned, for instance 2D flows like rectilinear unidirectional steady state 2D flows, and transient 1D flows that we solve for, oscillatory flows, the Stokes first problem, the Stokes second problem, all those things we have discussed extensively. And I believe that should be well enough to understand the chapter of 2D flows and transient flows basically. Okay, so we'll close that chapter now, and we will begin with a new chapter, uh, which is known as, or you can call it as a new what to say module, which is, so there's something known as creeping flows. And I believe you have solved a part of this problem. So you have solved something known as the Stokes drag, that you basically solve when you have a sphere that is subject to a uniform flow. What you did is you calculated the drag that the sphere experience when it is subjected to a uniform flow of magnitude u naught. Okay, so you derive the drag is equal to some 6 pi mu times the velocity u naught times the length scale, which is a, and that's that. So that drag that you calculate, those are actually known as the, I mean, so the drag that you calculate, that's known as the Stokes drag, and the equations that you solve for calculating the drag. So what you did is you are actually solving something known as the biharmonic equation, which involves the string function psi, because of the fact that the problem that you solve is axisymmetric in nature. But in principle, that biharmonic equation comes from the fact that you are actually solving the creeping flow equations. Okay, so what we will now see is we will little bit look into the physical aspects of creeping flows. How do we get the creeping flow equation? I will again show you from the dimensional version of the Navier-Stokes equation and then simplifying it and invoking the assumptions. So the creeping flow equations you get by invoking something. So what you say is that you say that your Reynolds number basically goes to 0. In this limit, any flows. So I hope you realize that when Reynolds number goes to 0, your inertia terms basically drops off. Okay, the contribution from inertia drops off, which means that any flows where inertia is typically insignificant, you can tell that the Reynolds number basically is close to 0 or almost 0, and then that all the flows which satisfies this criteria, these are known as creeping flows. Okay. uh, People sometimes call it as highly viscous flows. This is also one way of telling, because if your Reynolds number is very small, you can argue that if your viscous term is very large or very dominant over the inertia term, then also your Reynolds number basically goes to or approaches 0. Okay, that's one way of saying, but it's not always the case, because you can also encounter an object whose length scale is very much small. Okay, in that case also your Reynolds number, whatever be the viscosity, in that case also your Reynolds number will be very will basically go to 0. For instance, if let's say you are taking a moment of a microorganism that is moving through water. Okay, so you know that the viscosity of water is what, 10 to the power minus 3, I guess, Pascal second. That's the dynamic viscosity of water. But the length scale of the microorganisms is going to be of the order of, let's say, 10 to the power minus 8 or 10 to the power minus 9. Okay, in the nanometers, or let's say 10 to the power minus 6, at least in the micrometers. Okay, in that regime also, if you calculate the Reynolds number, you can very nice do a back of the envelope calculation. So your Reynolds number is going to be equal to the density of water, which is 1000, times the, let's say, some characteristic velocity which you can actually calculate. Let's say I have a microorganism which is moving with 1 millimeter per second, which can be any intrinsic velocity of the organism, having a length scale. So you can pick the length scale, or let's say the characteristic length, to be around 10 to the power minus 6, and mu is just 10 to the power minus 3. So if you can calculate the Reynolds number based on this data, you will see that your Reynolds number is very small. It's basically, so it's maybe your Reynolds number will come out to be around 10 to the power minus 6 or 10 to the power minus 7, whatever I mean, just substitute the values and then check the Reynolds number. So what you will see is that in that case, a small microorganism moving with a prescribed velocity, having a very small length scale, says that it's in the creeping flow regime. Okay, so that's typically why it's not always the case that you always encounter highly viscous flows to be only following in to be only having the regimes of creeping flows, but it's also the other way around, where you can have the motion of very small objects moving in moderate viscous flows to also be falling in the regime of creeping flows. Okay, that's typically because of the length scale. So all it matters, as I said, is that on this Reynolds number, and we will see. So what we'll see is we will see these creeping flow equations, and then going forward we will see something known as the consequence. So we'll see that the creeping flow equation that you derive, or the biharmonic equation for the stream function that you derive, you will see that they are indeed linear. Okay, so we will see something known as the consequence of linearity of these creeping flow equations. And lastly, if we have time, I'll just introduce something which is known as the spherical coordinate system, because we will be solving one problem, because I feel this is important in if you want to actually get a flavor of solving or of using the creeping flow equations, and to solve the biharmonic equation. Basically, a knowledge of the spherical coordinate system is also essential. And we'll not solve the problem today, because I don't think so I can finish that, but at least I'll give you a flavor of how the spherical coordinate system is, if we have certain time. Okay, so as I said, we'll now be moving into the creeping flow equations. And so let's get started. So we'll start off from the basic Navier-Stokes equation written in vector form, okay, and the dimensional version. So if I have, so for example, that's we have been doing this many a time. So if I have my velocity field, this is my dimensional velocity field, and I am so this is my vector field that I'm taking, which means that it can have components like, let's say if you're writing in cylindrical space, it can have. So for now, what we'll do is we will denote. So this is important. So we'll denote something which is known as the spherical coordinate system, although we'll not be using this in this derivation, but this is just for a heads up. So we'll be denoting the spherical coordinate system as r prime, theta, and phi. Okay, where r prime is the spherical radius, and we will see what all these things very shortly after we do this analysis. So this is so just keep in mind that this is the spherical radius, and in order to demarcate this from the cylindrical coordinate system, so we also have, remember, we also have our good old cylindrical coordinate system. We will write it as theta, or so now the cylindrical coordinate system will write it as rho prime basically. Okay, where rho prime is the cylindrical radius. Okay, don't confuse it with density. We'll call it as rho prime basically, or maybe what we'll do is, not let's not call it as rho prime, maybe we'll call it as capital R prime. Okay, where capital R is the cylindrical radius and small r is the spherical radius. Please keep that in mind. So we'll call this as R prime, uh, phi and z, where you can show that this phi and this phi is exactly the same, because that's the same azimuthal angle that we are considering, and z is the direction is the z direction. Okay, so the difference comes here is that this small r prime is the spherical radius. That is, you pick any radial vector from a spherical surface, the direction in which that vector points is in the direction of the spherical radius. While this capital R prime is not the spherical radius, but this is going to be our cylindrical radius, which we normally use, and we had been doing. So until now, we had been using small r for the cylindrical radius because we didn't encounter spherical coordinate system. But now, since we will be using spherical coordinate system, at least in the next discussion hour, the cylindrical radius will denote it as by capital R. Okay, I hope this thing is clear. Okay. This is my cylindrical radius, and we will see how the cylindrical and the spherical radius relates when I show you uh, the spherical coordinate system. Okay, but anyways, so the point is, if I now write the Navier-Stokes equation that is being governed by this vector field u, the equation will be what? So the equation will be rho times, where now remember this rho is the density, and don't confuse this with the spherical radius. Okay, and that's the reason why I said that don't confuse it with the cylindrical radius, and that's the reason why I said that the cylindrical radius is denoted by a capital R prime. Okay, but in some books, they generally write the cylindrical radius as rho and the spherical radius as R. But since we are using density, since you are using rho for density, I prefer to write the cylindrical radius as capital R. Okay,
Anyways, so the Navier-Stokes equation, as we all know, this will look something like this. It is del u prime by del t plus u prime dot grad u prime. Okay, and so this is going to be this, and then this is going to be minus gradient of pressure plus mu times del square u prime. Okay, so that's all. That's the Navier-Stokes equation that we are writing in vector form. That's what we had been doing. Okay, so this is the Navier-Stokes equation in vector form. Okay, see our objective. See, our objective should be clear. Okay, so the objective is we are interested in looking into what this equation would look like in the limit when Reynolds number tends to 0. And again, I said this is where non-dimensionalization comes handy to us, because now we know that the limit is in the terms of Reynolds number, while this equation is in the terms of dimensional quantities. This means that we must first convert this dimensional Navier-Stokes equation into a non-dimensional form, and then only we can use the limit Reynolds number tending to 0 into the equation, because the Reynolds number is a non-dimensional number, right? And we have a dimensional equation. So simply we cannot put non-dimensional limit into a dimensional equation, and this is a first-hand example where we see why non-dimensionalization helps actually. Okay, and the reason why I have been so stressing on practicing non-dimensional problems in addition to solving the dimensional equations as well. Okay, these are certain instances where it becomes handy actually looking into like the behavior of the equations, because typically the limits that we see in fluid dynamics, these are generally established in terms of non-dimensional variables. Okay, because these makes the problem generic, as I insisted on when we were trying to understand the characteristic scales in our problem. Okay, so let's then quickly non-dimensionalize this equation. Now I believe you guys are master of non-dimensionalization now after doing several problems. So I can then pick up a non-dimensional velocity vector field u, which is equal to u prime by uc. Okay, where uc is the characteristic velocity. Uc is the characteristic velocity. Okay, I can also choose something known as t, where this t is nothing but my time scale, the non-dimensional, or sorry, t is nothing but a non-dimensional time, and this is nothing but the dimensional time by the characteristic time, and we will choose the characteristic time. Okay, so we'll choose this later on. Let's just keep it as tc. So we'll call it as my characteristic time scale. Okay, so this means that I also have a length scale lc. So this is my characteristic length. Okay, and then I can define. So then I believe you can understand that my gradient will just change. So the dimensional gradient will just change to, sorry, the non-dimensional gradient will just be equal to the dimensional gradient by LC. Okay, right? Because this gradient would be what? Del del x prime of ex plus del del y prime and so on, which means I can bring out the LC and then this becomes del del x just. Okay, so then that's why I wrote this is so sorry, I just wrote the other way around. So no, I guess it's fine. So the non-dimensional gradient is going to be the dimensional gradient by the characteristic length. That's how it goes. Okay, so then if I just substitute if I just substitute these for example, I can then write oops, sorry. So for example, I can write now u prime in terms of u. So I can then write u prime is equal to u times uc, and that's all that I have been doing. So then this becomes equal to what? So this becomes equal to rho times uc. So rho I'll take it outside maybe. From here I will get what? So from here I'll get uc by tc. Okay. So it's going to be uc by tc times del u by del t, plus from the second term I'll get uc squared by lc times u dot grad u. Okay, from pressure I'll get minus pc by lc, where I'll call pc as my characteristic pressure. Maybe I'll write it down here. So pc is my characteristic pressure. Okay, so this is going to be pc by lc times gradient of p plus mu uc by lc squared del square v. Okay, that's it. That's the non-dimensional equation by taking out the scales basically. Okay. So now what we'll do is we will do certain things. First of all, we will choose the characteristic pressure as mu uc by lc square, which is nothing but the viscous scale. So remember, I told you pressure scales has two ways. One, the inertia scale, which is rho uc squared, which we have used in the previous example. Here we will say that pressure scales as the viscous scale. The reason behind is again very very obvious, and this comes from the physics of the problem, because we know that in the creeping flow regime, I know that my viscous force is going to dominate over the inertia force. Okay, that is only when you have Reynolds number basically going to 0. Okay, or in other words, the inertia itself is so small that the viscous flow that the viscous force will anyway dominate over this inertia force. Okay, in that context, the gradient of pressure is solely dictated by this term. Okay, I mean this mean, or in other words, in order to have equality in this equation, this term should roughly balance this term. That's one way of saying that why, or this one, you know what to say, this is one explanation of saying why your pressure scale says the viscous scale, which means because see, that this term will anyway approach to 0, which means this term has to dominate this term if we want to have a 0 or a tending to 0 thing in the left hand side. Okay, and that's the reason why your pressure should actually scale as viscous scale in creeping flow, in the creeping flow analysis. Okay, so this means that I'll choose PC as mu uc by lc square, which is nothing but the viscous scale for pressure. Okay, so if you do this, so then what does this term become? Okay, so let's see. So this is 1 upon LC, and PC is mu UC by LC squared. So then this equation becomes what? So this equation becomes rho times uh, UC by TC times del U bar by del T plus UC square by LC. Okay, U dot grad U. Okay, and this is equal to, remember this term will now be equal to minus of mu UC by LC squared, sorry, LC cube, because I already have an LC here. Okay, and then this is going to be gradient of pressure plus I'm going to have this term mu UC by LC squared. Okay, which is mu UC by LC squared. Okay, all right. Hold on, I'm just checking the chat progress. Let's see. Okay, I believe this is correct. Then just 1 second. I think I made a mistake in one of the powers of LC. Uh, let's see, where did I do the mistake? So this PC by LC. Okay, yeah. So I think that's the mistake. So PC is going to be, okay. I think that is what I was making. So PC is going to be mu UC by LC. That's the viscous scale, which means PC by LC is going to be equal to mu UC by LC squared basically. So this is going to be mu UC by LC squared. Sorry for this mistake. So viscous scale is mu UC by LC and not LC squared. Okay, so that's why when you write PC by LC, it becomes mu UC by LC times 1 by LC basically. Okay, so then it becomes mu UC by LC squared, and we basically have this term. Okay, all right. So then this is mu UC by LC squared times del. Okay, so this is del squared of U. Okay, so what I will now do is I will basically multiply. I will multiply by LC squared. So what I'll do is I'll multiply it by LC squared by mu UC. Okay, throughout the entire equation. Okay, so if I do that, let's see what we get. So we get rho times UC by TC times okay, let's see what we get, times LC squared by mu UC. That is okay. And then I have UC squared, okay, by LC times LC squared by mu UC, okay. And then I have okay, so I also have this term. I forgot to write this term here. So this is going to be del U bar by del T. This is just non-dimensional. And then I have U grad U. And right hand side, I'll not have this term because I've already multiplied by LC squared by mu UC. So this term is just going to be giving me 1, and this term is also going to give me 1, which means in the right hand side, I'm just going to have minus gradient of pressure plus del square of U. Okay. Now what I will do is, first of all, let's choose a time scale. So what I will say is, I will say that my time scale is going to be equal to the length scale divided by the velocity scale. Okay, that's so that so this is nothing but this the critical, I mean the typical time scale that we take, that is my velocity times my time scale is going to give me my length scale. So I choose my time scale, which is my character. So this is LC. So I'll choose my time scale as my characteristic length scale divided by the velocity scale. Okay. So then if I just substitute this thing, in fact, this is also known as the advection time scale. Okay, this is also called sometimes as the advection time scale. Okay, so if I substitute this time scale here, I'll get what, rho times uh, UC squared, because I already have an UC, divided by LC. Okay, times LC squared by mu UC. Okay, and then I have this term, which is del U bar by del T, plus if I do a simplification of this term, I'll have UC and UC getting cancelled, LC and LC getting cancelled, which means I have UC LC by mu times U dot grad U. Okay. And then this is going to be equal to minus gradient of pressure plus del square U. Okay. So what I will now do is I'll bring the rho inside, and also I'll simplify this term as well. So this is going to be LC and this is just going to be this. Okay. So what I'll do is I'll bring the rho inside. Okay. And then this, okay, then this term is going to be what? It is going to be rho times UCLC by mu times del U bar by del T, plus I am going to get rho times UCLC by mu times U dot grad U, and then this is going to be equal to minus gradient of P plus del squared U. Okay. Now, this is a well-known number, right? This is just going to be your Reynolds number corresponding to the chosen length scale. Okay. And this is also going to be your Reynolds number. Okay. And that's exactly what we are seeking for, right? We are trying to bring in Reynolds number to this expression such that we can set the limit Reynolds number going to 0. Okay. So then I can write this as Reynolds number taken to be common as del U bar by del T plus U dot grad U. And then I have minus gradient of P plus del squared U. Okay. And what I'll do is I will, okay, so now, yeah, okay, so that's it. That's the non-dimensional. So this is the non-dimensional Navier-Stokes equation, non-dimensional version of the Navier-Stokes equation, where you see that you have all the non-dimensional variables, okay, and the Reynolds number now. So now it becomes very easy. So what I will now do is I'll just take this limit Reynolds number tending to 0 into this entire equation, which you can bring it here. And if you do this, what you will simply get is this term will just drop out, and you will have just this equation, right? Minus gradient of P plus del square of U is equal to 0, and this equation, and also remember you also have the continuity equation, which is divergence of U equal to 0 for an incompressible fluid. Okay, so this equation, this is a very powerful equation, which we call it as the creeping flow equations, or sometimes it is called as the Stokes flow equation. These equations in the limit, remember you are using, so what you are doing is you are basically invoking the limit Reynolds number tending to 0 in the Navier-Stokes equations. to basically get these equations, which we call it as the creeping flow. So they are sometimes called as the Stokes flow equations, or creeping flow equations. Okay, so this seemingly simple equation, see you see, so far there are a couple of things. Okay, first of all, you now understand the power of non-dimensionalization, right? Sorry, because you know that now, since you know that the condition was Reynolds number 10 into 0, all you require to do it just derive the non-dimensional version involving the Reynolds number, and then just set Reynolds number to be going to 0, which means what you essentially saw is that, see, the Navier-Stokes equations are become non-linear because of this convective term, okay, u dot grad u. But in the limit when Reynolds number basically goes to 0, you essentially lose the non-linearity of the Navier-Stokes equation. So these Stokes flow equations that we wrote, or the creeping flow equations, they are essentially linear, which is not the case if we are actually solving the full Navier-Stokes equation. Okay, so these are linear in nature. That's the number one thing. And essentially, this linearity has very important consequence. So I'll underline this because this is so important, that this linearity of the Stokes flow equation, or the creeping flow equation, has so much interesting consequence into the dynamics of the fluid, or if you want to see the dynamics of a body that is moving through a fluid. Okay, and maybe we'll look into some examples. Uh, maybe look into some examples today, if there is let's see if we have time, we'll look into some examples today of the consequence of linearity of this creeping flow equations. But yeah, so that's the thing. So so what you do is, you basically see that, okay, since you are dropping the inertia term in the limit when Reynolds number going to 0, this essentially makes the creeping flow equations to be linear. Okay, this is one aspect. Okay, the second aspect is, so what you did when you are actually solving for the Stokes problem is that, so you have this equation minus gradient of P plus del square u equal to 0, and then you have divergence of u to be equal to 0. So what you do is, now since we have two unknowns, so remember we essentially, so vectorically we this u is so if so what I'm trying to say is, this u is a vector, it's a vector field, and it have basically three components in 3D space. So I have three unknowns. Okay, and also this pressure is not known, right? So this P is also an unknown, which means from this I actually have four unknowns. Okay, and also I have four equations, right? Because this equation is a vector equation, I can get three equations from this, and I can get one equation from the continuity equation, which is a scalar equation, right? Which means, in principle, in order to completely solve for this pair u and P, where, remember, u is a vector field, meaning that it have three unknown components, I actually need four equations to basically solve for the velocity field and the pressure. So now there's a clever way of actually reducing the number of unknowns into one just single unknown, which we call it as the stream function approach. Okay, and this you have been doing in order to derive what is known as the Stokes drag, as we have been discussing. So what you do is, you basically take curl of this equation. So if you take curl of the Stokes flow equation, and define something which is known as the vorticity, which is nothing but, so what you do is, you define this del squared u, okay, as minus omega. I think they take a minus omega here, that's just the sign. Okay, so if you define these two, and then what you do is, you define something which is known as a stream function. Okay, because you know that if your and for 2D problems, I believe you know that for 2D problems, you know that if your fluid is incompressible, you can define something which is known as the stream function. Okay, in 2D problem, the direction of stream function is immaterial, because it actually faces, so your stream function basically comes from the fact that it is basically curl of the velocity field. That's how you can actually define the stream function, and it basically so it basically satisfies the continuity equation, because if you define stream function, your continuity equation is trivially satisfied. And you know that you can actually define a stream function for 2D flows, uh, and then use the fact that if you take curl of the Stokes flow equation, so I'll just give you the just the just the overview. So if you just take a curl of this, so what you'll get is, you'll get curl of grad P plus curl of del square u equal to 0. Okay, now we know that curl of gradient, curl of, gradient of a scalar is equal to 0. Okay, which means you just have curl of del squared u equal to 0, and you define there is something known as del squared u equal to minus omega, where omega is nothing but the vorticity. So then your vorticity satisfied, del square omega is equal to 0. Okay. So what you do is you first solve for vorticity, and from vorticity you basically calculate the stream function. Okay. You can relate basically vorticity, the velocity field, and the stream function. So the ultimate equation, I'm not writing it down. So the ultimate equation you get is something like this: del power 4 times psi equal to 0 for the stream function. Okay. And so what people do is, instead of solving these four equations, that is the creeping flow equations and the continuity equation, people, what they do is they write the equation in terms of the stream function, using this fact that you take curl of the Stokes flow equation and use and define the vorticity. And then what you need to do is you just get a single function. So this is a single equation that governs psi. Okay. So instead of solving the four equations in order to get the velocity field, what you do is you just solve this single equation, because defining, as I said, defining stream function means that it just gives you the fact that the continuity equation is trivially satisfied, which means you don't have to care about the continuity equation, and you just need to solve one equation, which is basically this equation. And this equation, this is known as the biharmonic equation. Okay. And so the advantage, as I said it, I agree, this is the higher order equation to the Stokes law equation that we had, because the Stokes law equations were second order, but I understand this is fourth order. But you don't need to solve four equations. So instead of solving four equations, you basically need to solve only for the stream function, because once you know stream function, you can get the velocity field, because you know the relations, and also you can get the pressure field from the momentum equations basically. Okay. So but this analysis, this is just limited. So this is just limited. So whatever we have written here, this is just limited to 2D or axisymmetric problems, because that is where the realm of stream function is actually. Okay. So for only 2D or axisymmetric problem, you can actually solve this biharmonic equation and get the value of stream function. Okay. But the important thing is, you generally have boundary condition in terms of velocity. What you need to do is you also then need to write the boundary condition in terms of stream function. Okay. So solve this equation subject to the boundary condition that the stream function will take at the boundaries, will uniquely give you the actual stream function that we're actually looking to solve for. And once you know the stream function, you know basically the velocity field by using the relation between the stream function and the velocity fields. Okay. uh, that's the idea. For example, once you know psi, you can write psi as just del u del y, right? So once psi is known, you can integrate it to get u basically. That is the x direction velocity. And similarly, you know that your psi is equal to minus del v del x. Okay, so once you know psi, you basically also know the v component or the y component of velocity field. Okay, that's so that's the overall idea behind using this stream function. Okay. Okay, that's so that is it. So maybe what I will do is I will not go into the consequence of linearity of the Stokes law equation. This is something that I will discuss maybe in next class, or if we don't have time for that, I will post that separately in the discussion forum, and you can you can go through the consequences of linearity of the Stokes law equation. So these are certain examples which actually shows that how powerful is basically the fact that the governing equations are linear can actually lead to at least get qualitative insights of the problem that we are looking to solve for. So these are some examples which shows. So basically, it just shows that the linearity idea of the Stokes law equation is actually very powerful in getting certain insights into the solution that we're actually looking to solve for by actually solving the problem. Okay, but we'll not do today now because of the lack of time, because I have certain examples that I plan to show. Instead, what I will do is, so these are the examples of the consequence of linearity, so I'll leave this now. Instead, what I'll do is I'll close this discussion by actually looking into the spherical coordinate system that I was actually telling you. Okay. So because what so the idea is, the reason why we are looking into this spherical coordinate system is, in the lecture series I think we have solved the biharmonic equation by using the cylindrical coordinate system. But what I will do is in the discussion hour, I will show you that you can also use a spherical coordinate system and then solve the biharmonic equation to get the solution for stream function. And we will actually solve a problem, a prototypical problem, where there is a sphere that is moving in a parabolic flow. The sphere is uh, aligned with the central line of the parabolic flow, meaning that we are not looking into the offset distance. That actually doesn't become a 2D or an axisymmetric problem in principle. But if we have a sphere that is moving just in the same direction as that of the flow, and if the sphere is located in the center line of a parabolic flow, then you can actually solve this problem using the stream function approach. But for that, you need to know how the spherical coordinate actually operates on, okay, or you need to know the spherical coordinate system, okay. So for that, we'll little bit give you a flavor of the spherical coordinate system. So we have, this this Cartesian system. For instance, this is Z, this is X, and this is Y. So the spherical coordinate system is something that you can think of by, imagining a sphere whose center is basically located at x comma y comma z equal to 0 comma 0 comma 0. For instance, the center is located somewhere here. Okay. So you can just imagine this to be a sphere. So you can basically imagine this red surface to be a sphere whose center is at the origin. Okay. And then what you do is you define something known as the spherical radius, as I was telling. So this is r. Okay, and the angle that this spherical radius makes with the z axis, we call it as theta. This theta is known as the polar angle. Okay, and this r is nothing but my spherical radius. So it is like you pick up a tennis ball, and any radial vector pointing outwards of the surface of the tennis ball will be your spherical radius, basically. Okay, that's how you can interpret your spherical radius to be. And any orientation or any deviation of that spherical radius from the z-axis, you need to define that by giving a certain angle theta with respect to the z-axis. Okay, the theta is known as polar angle. Okay. Now, what is this? There is one more angle that you need to understand in spherical coordinate system. For that, what you need to do is you need to project this spherical radius onto the xy plane. Okay. So if you project this onto the xy plane, you understand you are actually now looking into an equilateral plane. You are actually now looking into an equilateral plane of this form. Okay. My handwriting is not so. Okay. Maybe maybe I'll not show it here because this drawing is not so correct. I mean, not so correct in the scales. So, well, so what I believe you understand that what you are doing is you are kind of taking. Okay, what I can do is I can actually draw. I have tools here. I can actually draw a sphere basically. That in that way, I think things would be much more. Okay, I'll just erase this. Wanted to draw it in a more better way. Okay, just bear with me. So I'll just erase this as of now. Okay, so what I'll do is maybe I'll draw a circle here. Okay, this looks good, much better. And then this, as I said, this is my this this is my r, this is my theta, and then on the xy plane, what I'm actually looking for is something like this. So okay, I'm actually looking for in the equilateral plane. What you can do is you can maybe do something like this. Can maybe do something like this. Can maybe do something like this. Okay. Okay, I think this is much better in terms of the drawing, thanks to the tools that I have. Okay, so what I'm actually doing is I'm actually projecting, this spherical radius onto this plane. Okay, so what I'm doing is, I hope you can understand that I'm actually projecting, and remember this R is in the 3D plane. Okay, maybe if I draw this R in this way, it will be much more better off. Okay, maybe what I do is I will kind of draw this R like this. Okay, so this R is something like this. This is my R. Okay, and I believe this is theta. Okay, so it's a kind of a 3D thing that we are drawing, and okay, no, now so it's not right basically. It's very difficult to draw a 3D thing, you know, on a 2D surface. So hold on, just give me some time. I'm extremely sorry for this, but actually I want to make it look clear so that I can show you what this system actually is. So what I'll do is maybe something like this. Okay, I think now it's much more better. Okay. Anyways, okay. So this is R, as I was telling. Okay, I'll not bore you with my bad drawing anymore, but let's try to work on whatever we have. Okay, so this is my R, as I was telling, the spherical radius. This was my angle theta. Okay, so now what we are doing is we are essentially taking the projection of this R on this blue plane. Okay, so this is the blue plane. So this blue plane is something which so I hope you realize that this blue plane is in the XY plane. Okay, right. So what I'm doing is I'm taking the projection of R onto this blue plane, and then I'll get this distance. Okay, basically I'll then get this distance. So I hope you realize, if you pay a little bit of closer look, that this blue arrow, we call it as capital R, and this capital R is nothing but the cylindrical radius, because you know that the cylindrical radius always lies on the XY plane, right? So this capital R is nothing but your cylindrical radius. Okay, and you then can say that this is equal to the small r times the sine theta, right? And from here you can also interpret that your z is equal to r times cos theta. Okay, so the Cartesian z is equal to the spherical z times cosine of the polar angle. The cylindrical radius is equal to the spherical radius times sine of the polar angle. Okay, then this angle that this projection of r makes with the x-axis, this is something that we call it as phi. And this phi, this angle phi, this is known as the azimuthal angle. So this is known as the azimuthal angle. Okay. Okay, which means if I completely determine this r, theta and phi, I can actually generate any spherical surface or any spherical volume in space if I uniquely know what is r, theta and phi. And this r, theta and phi together, they constitute the spherical coordinate system. Okay, so just like the cylindrical coordinate system, just like the Cartesian coordinate system, this r, theta and phi will, as I said, this will uniquely give us a spherical volume at a, let's say, at a particular r, at a particular theta, and at a particular time. You basically get a point in this spherical space, and collection of all this will give you a spherical volume. Okay, and this is sufficient to give you, or this is sufficient to give you a coordinate system. In fact, this is an orthogonal coordinate system. You can see that these vectors, that is e theta and this e phi, these vectors are mutually perpendicular to one another, which means that just like cylindrical and Cartesian space, this is a orthogonal coordinate system. But this is a curvilinear system that we are actually working on, just like the cylindrical system. Okay, so that's typically is your spherical coordinate system, and you can draw certain. So you can actually relate the spherical coordinate system with the Cartesian coordinate system. One relation we know that this r is equal to r is basically equal to, so z is equal to r cos theta. You can use one more relation. For instance, this r is nothing but r sin theta, right? So then my x becomes this capital R cosine of phi. But I know that capital R is equal to r sine theta, which means x then becomes r sine theta cos phi. And similarly, you can show that your y becomes r sine theta sine phi. And z, you know, z is equal to r cosine theta. So this is then a simple relation between your Cartesian and spherical coordinate system. Okay. Similarly, you can also draw a relationship between spherical and cylindrical. For example, your cylindrical radius r is equal to spherical radius times sine theta, that we already know. Your cylindrical phi is equal to, so your cylindrical cylindrical angle is just the azimuthal angle basically. Okay, so then theta is just basically equal to theta, which means in the cylindrical space this angle is just the azimuthal angle. That's it. And your z, you know that your z is just equal to r cosine of theta. Okay, so this is a relation, as you can see, between the spherical space and the cylindrical space. Okay, okay, that's it, that's the relation. And what we'll be doing is, so the idea is, so the reason why I have discussed about this spherical coordinate system is, I will actually try to solve this problem del 4 psi equal to 0 that we have solved using spherical coordinate system, in spherical coordinate system in fact, and then try to solve for the velocity field that is generated when a sphere or a ball, or let's say a spherical object moves, uh, let's say in some particular moves, let's say along a particular direction when it is subject to a parabolic flow. Okay, that is a problem that we'll try to solve. So what we'll do is, eventually we'll try to solve for the velocity, at what velocity will this sphere move when it is subjected to a background parabolic flow. We'll try to solve using the spherical coordinate system. Okay, and we'll see that that problem is an axisymmetric problem, which means that indeed we can use stream function into writing our solution. Okay, so that's it guys. That is something that we plan to do in the next class. So as I said, this Saturday, please try to note that this Saturday we'll not have any class. This class that we are taking today, this is a adjustment of the class that we are supposed to have on Saturday from 3 to 5. We'll not have the class on this Saturday. But remember, rest of the class, it will always be on Saturdays from 3 to 5. For instance, the next class that we'll have is so that will be next week on, the next Saturday from 3 to 5 basically. So only this Saturday we are not having any class, and the compensation class is this class that we currently had today, from basically 7 to the whatever time that we are doing. Okay, that's the compensation class for only the Saturday that is to come. But the rest, everything else will always be the same, that is on every other Saturdays from 3 to 5. So the next class will be on next week, not this week, the next week Saturday from 3 to 5. Okay, please don't confuse with that. Anyway, you will be intimated through emails prior to having the discussion hour. Okay, as already you guys know, basically you get emails before the discussion hour. Okay, so again, the class this Saturday only we are not going to have the class, and this class is a compensation class for this Saturday's class. The rest, everything is going to be on the normal time. That is, we'll meet on the next week Saturday from 3 to 5 p.m. as we already, or as we normally do in all the other classes. Okay. All right. Then thank you very much. We'll meet in the next class.